trial stuffs. Yeah, that kind of stuffs. So basically what we are going to go through is alternating current. We'll also go through the capacitor, inductor, and impedance, that kind of stuff today. Okay, so all of them are math and calculations. And we will also go through the resonance circuit. So it is important, as we have to know there is a circuit in our radio which we tuned the desired frequency to receive. And this part of the tuning circuit is actually LC parallel circuit. Yeah, we connect the inductor and capacitor in parallel to choose the correct frequency we want to use. Okay, so this part is more theory stuff once again. And once we go through lesson 5 and lesson 6, we'll go to about the signal transmission. Okay. Oh, so AC. So why we are going to talk about AC? AC, you know what is the alternating current, which is the current, the voltage will flip from time to time. They will flip from negative to positive. So the frequency change is called, how should I address it? The time it requires to change is called frequency. Okay. We say that here you can see reverse is polarity, which is flipping from positive to negative. Okay, and this side is also switching from negative and positive. Okay, and this is we call alternating current. So we've got a comparison here for a perfect DC, perfect direct current, like a battery output. You will see the current and voltage output is constant, a straight line. Okay, a straight line. But if you are using a perfect DC will have a sine wave-like curve. The current and voltage will also looks like a sine wave. We are not going to go through too deep on the phase change. Okay, if you are very familiar with the physics stuff, you know that the voltage and current in DC is differs by 90 degrees. But we are not going to go through this. Okay, we will just know that in your exam you will just have to know alternating current, sine wave. That's all you have to know. Okay, we don't have to go through year 1 physics. Don't worry. This is an illustration how it looks like actually. Okay, so you can think that the voltage is rotating in a cycle, and this line is actually the time. Okay, the time. So if you rotating in a circle, you'll get a sine curve. This is why the reason why we have a sine curve in our from our when we measure it. Yeah. Okay. We have to go through once again the right hand rule. Let me turn on the fan a bit first. Actually a bit hot. Okay. Fleming right hand rule tells us that induced current we call it FBI. F is force, B is the magnetic field, B field, we call B field, magnetic field. Okay, they don't have the word magnetic here. So the B actually is the NS here, the magnetic field. Okay, and the middle finger is FBI, current. Okay, current. So this right hand, this left hand, this right hand rule, this right hand rule helps us to calculate and know the direction of induced current. Okay, when we have a wire moving through a B field, an electric and a magnetic field, we will have induced current in this direction. Okay, B field, NS, which is this, the current, then the moving direction is like this. Okay, let me see. FBI. Okay, so your motion is like this. You have the wire move in this way, move across the magnetic field NS, which is point like this. So you have the induced current from here, okay, moving from here. So why we have to go through this is because you know that electro and electromagnetic, they come into the one word. So magnetics can help to change into current, and current will generate magnetic field. So I have to explain to you first. So we have an AC generator here. Let me have a quick look. AC generator is basically a use of the the use of induced current. So you have a wire moving in a B field, and we have the generated current from here, okay? And the current from this motor, from this generator will generate a sine curve, the electricity in a sine curve, okay? So we call it the AC generator. Okay. So still high school stuff, right? Should be easy. And we use 220 volts. We got three-phase electricity in Hong Kong, but we just talk about single phase today. Okay, for single phase electricity, we use 220 volts and 50 hertz. But not all the countries in the world use 220 volts and 50 hertz system. Okay, and when we talk about 220 volts, we just talk about the socket at home. So do you know why we don't use 220 volts for the transmission? Why? So I try to recall your memory of last lesson. So you still remember what is Ohm's law, right? V equals to I out, right? So if your so we got actually resistance in our all transmitting wires, right? The wires may have a very if we have a very good conductor, but we have a very long pieces. So last time we called the resistivity, right? When the wires become very long, the resistance of it will become very significant. So the values will grow very large, okay? And using this 220 volts, but the R become very large, the current will drop. We want our wires to help us to transmit a very strong current, so our voltage will go up. Okay, so that's why we have to compensate the resistance. We try to use the voltage as high as possible. So for the transmission line in it is like 1,100 volts, 1,100 volt VOLT volt, and or even more higher. Okay, so that's why you know Ohm's law. It applies anywhere. It may apply in your exam, right? You have to remember it. As we have just talked about, not every country in the world use a 220 volts and 50 hertz system. So do you still remember what is 50 hertz? I haven't mentioned it here, but I have mentioned it last time. So 50 hertz is the polarity of the AC changes 50 times per second. This is we call 50 hertz. And if it is 60 hertz, it means the polarity changed from positive to negative 60 times a second. Okay. So if your adapter is not saying that it is a 50 or 60 hertz, or the voltage is not 120, 200 to 400 volts, which is because it is self-adapt. It can adapt the voltage itself. Okay. If you don't use a adapter like this and you go to travel, your adapters may burn, may be damaged. Okay. Like in our device list in our radio room, actually we got a power supply which operates only in a DC, a transformer. No, it is not a transformer. It's a rectifier, okay, which converts from AC to DC. Because the rectifier works with 110 volts. 110 volts. So if we accidentally connect it to our main circuit, it will burn out. Okay, it will damage. So make sure that if you bring your chargers to other countries, make sure it is 100 to 240 volt, and the hertz is 50 to 50 or 60 hertz. Okay, so if I just talk about period and frequency. Frequency is numbers of occurrence of a repeating events per unit, blah blah blah. Okay, in the world of electricity, it means that the voltage here, okay, the amplitude flips from positive to negative 50 times in 1 second. It is 50 hertz. If it is 60 times, then it is 60 hertz. Okay, so the notation we usually use frequency, F. We denote it as F, and the unit is hertz. So if we are not talking about the frequency, we talk about the period. The period is how long does it take for the sine wave to finish one cycle. Actually, it is just the reciprocal. Frequency is just the reciprocal of period, or in reverse. Period is the reciprocal of frequency. But sometimes they you use this kind of conversion from time to time. When we talk about the wavelength, especially when we talk about the speed of light, okay, the electromagnetic wave. So we will do this kind of conversion many times. Okay, so I have an example here, how to convert 60 hertz to seconds. So you know that our electricity use 50 hertz or 60 hertz. In Hong Kong, we mainly use 50 hertz. We don't have 60 hertz. We don't normally use 60 hertz. Okay, most of our devices use 50 hertz. So like in Japan, they use 60 hertz. 60 hertz, so you can calculate 1 over 60 is 0.016 seconds, right? Or 167. Okay, when you round it up. So it is 60.6 milliseconds. So last lesson we have talked about how to convert to SI units, right? Milli means divide by 1000. So it's 0.016 divided by 1000 is 16.6 milliseconds. We got some more knowledge for you, but it is just for your reference. Okay? You don't have to memorize it in your exam. Sometimes when we touch the headphone jack, we may hear a hissing sound. This is because we short our electricity with ground, so that you can hear us. In Hong Kong, we can hear a 50 hertz sine wave sound. Okay, this is why we have the hissing sound. If your grounding is not doing it correctly, you will hear that kind of sound. So if you go to another country and you touch your headphone jack, you can see a higher voice, a higher pitch. This is because they use a higher frequency. They use 60 hertz. So actually, they got a YouTube video talking about if you hear how can you hear the sound of electricity, a 50 hertz sound and a 60 hertz sound, by just touching the headphone jack. Yeah, and just because a 50 hertz and 60 hertz is in our acoustic range, so we can hear the sound. If they use a higher frequency, just like our radio, they use 1000 hertz or megahertz, we can't hear the wave. We will just hear it. It's beyond our acoustic range. Okay, that's why we can't hear them. So we have some more terminology to go through. Amplitude. We have to go through amplitude. Amplitude is how we measure the peak. The peak. Okay. You can just simply think it as a peak-to-peak value. The sine wave, okay? The range of the wave, the peak-to-peak. Sometimes it may not be as perfect as this one. The electricity may not from zero to what I mean is the sine wave may shift on the y-axis. They may shift higher or shift lower. So when you measure the amplitude, just measure the peak to peak. Okay? Oh no. It should be peak to peak divided by 2. Okay? Once Let me go through it once again. Zero line indicates the larger positive amplitude. From zero to the peak amplitude, zero to the negative peak, negative amplitude. Okay, zero to positive, zero to negative, which is the peak value. It is just the same as the peak value, not peak to peak. Peak value. Okay, peak value. We will have to go through this kind of terms in our lesson. Peak, peak to peak, RMS, and average value. So we have one whole slide to go through all the stuffs. Just kidding, I'll go through them one by one. So it is for your revision. I will go through it deeper. So this one, it is the peak value from 0 to the maximum point. It is peak value. So from 0 to the negative point, it is the negative peak. It's just the peak. It's also the peak value, but just the reverse sign. Okay, in the reverse way. In some textbooks, they will call that the peak to peak value is 0, but we will follow ARRL, because ARRL is our reference book. The peak to peak value will be the highest value minus the lowest value. Okay, so in this case, our sine wave, which is 2 times the peak value. Easy, huh? Peak value equals to 2 times peak value equals to peak. Okay. So I'll have to go through the RMS value. What is RMS value? So you have to just memorize peak value is equals to RMS is equals to peak value times 1 over root 2, which is 0.707. Okay, so we call it the RMS is the effective voltage of okay, so you know that this AC is actually goes with a sine wave, right? So how is what is the corresponding voltage of the DC? So we have to measure the AC. What is the voltage in terms of DC? Okay, we want to compare it with DC. So we use the RMS value, root mean square value, to measure it. Okay, so actually you can see that it is the root mean square of any time. Okay, so we actually, by definition, we do integration here. Things like integration. We take every point of it, take a square, and try to draw a line. Okay, so you know the line is around is here, 1 over root 2. So it is from definition, and we don't make it up a value. Okay, so if just in your exam, just memorize it is 1 over root 2. Okay, so I want to go deeper, a bit deeper. If you it's one day, if you encounter a wave, it is like a square wave or a more weird complex waveform, you do the same thing. You take every point of it, square and over n. Okay, so if you do integration, you just take this formula. So if you have a complex waveform, it is no longer 1 over root 2. But sine wave, you can just memorize 1 over root 2. And sine wave is the only wave you see in your exam. You won't see complex waveform. Okay, you just see sine wave. So you can just memorize 1 over root 2 RMS or 0.707. Okay, at that time I memorized it because I think root 2 is easier to memorize. Okay, so this is we want to compare the effective voltage of AC with a DC. So if you have a chance to measure the AC current with a multimeter, you have to flip your meter to measure AC. If you measure DC, you may sometimes measure the peak value, which is like around 300 and I forgot, you can just multiply 220 multiplied by root 2, which is for 340 something, as I remember. So you may read the value like 340 something. It is the peak value, so you do it wrongly. Okay. Average value, we take the average of the half cycle. Okay, half cycle. So you know that we take this value. So if you don't want to go through the formula, just remember that average value equals to peak value times 2 over pi, which is 0.637. And we just take this part, okay? We just take this part and do the integration here. We do the average. So it is take every point of it and divide by t. Okay. This is the definition, but yeah. But in your real life, RMS is more useful than the average value, but you have to know it. I don't know why yet, but this is one of the definitions we use, okay? Average value of each AC half cycle in the mean, which is average, mean means average of all instantaneous value in the half cycle. Okay. So once again, the 2 over pi just applies in sine wave, which is a perfect AC. If you are not doing the AC once again in your high school or university math, you have to use this formula. Okay. Especially you do the signal stuff, so you have a lot of torture. Okay. Let me have a quick check first. I want to have a look at how many slides I have to go through. Okay. Let me go through the slides again later. So I will introduce phasor to you first. So phasor is, we can denote every perfect sine wave in this form. Okay, V means the amplitude, which is the peak value, okay, of voltage. So Vt is the we can express voltage at any time point in this formula. Okay. So omega is angular frequency, which is 2 pi f. So I will just use this formula to explain it. 2 pi times frequency times t. So actually you know that AC, a perfect AC goes with a sine wave. So this part is denoted at any time point, it is the peak value multiplied by a sine value, okay? And this theta here is the starting angle, or the initial angle, okay? Sometimes they may ask you questions like this and ask you, hey, I have a sine wave here like this. They may give you the initial starting angle and ask you at what time point, what is the instantaneous voltage of it, okay? So you have to apply this formula, knowing that what is the frequency of the AC or the signal. Sometimes the signal may not be a perfect AC. They may give you signals like our transmission, our carrier wave, which is like megahertz level. So you just have to apply this formula in it. But this question may just appears once, maximum. You won't see this type of question twice, because you just have 100 questions, and at least 40 of them ask you about the laws and regulations. So you know that's how much they can ask you about the mathematics. Not much, right? But sometimes they may ask you more the concepts, the mathematical concepts or physics concept. So you may have to memorize it, but they may ask you in a conceptual way. I don't know how they can ask it, but you have to know that AC sine wave. Okay. Actually, you may argue that, hey, can I say that it is a cosine wave? Yes, you can, but in our reference book, they use sine wave, so we follow this tradition. Okay. In some textbooks, they may call it is actually a cosine, especially when the current and voltage is different by 90 degrees. So sometimes you may see some textbooks or Wikipedia. Actually, I do some preparation and check Wiki. Wiki said that it is cosine. Okay. Just follow ARRL. Actually, it doesn't matter. So you know, sine wave and cosine wave is just a phase shift of 90 degrees, right? Oh, I won't go too deep. Right. You may worry too much of it. Okay. So sine wave actually looks like this. A means amplitude. Okay. So in this formula, I just use V. use voltage to explain it, but actually it also apply in voltage or current. Okay, amplitude is sine omega t. Omega means at every time point the frequency of it. Okay, 2 pi f. If you can remember the angular frequency, it is 2 pi. 2 pi f. 2 pi f t. 2 pi f t. Okay, 2 pi means 1 cycle. How long does it take to finish 1 cycle? So angular, because we travel the electricity travels in circle like this. So actually why we use the angular frequency. Okay. Let me have a quick check. Okay, easy. More terms to introduce. We use lead and lag. Okay, lead and lag. Lead means which one goes faster. Okay, sometimes we may have to compare two two sine wave or two AC. Okay, so if or as I've just mentioned earlier time, current in our AC, voltage is faster than the current by 90 degree. So we call it is a lead by 90 degree. The voltage lead current by 90 degree. Okay. So if it is faster, then we call it lead. If it is slower, then we call it lag. So actually lead and lag is the same thing, but it is one is about faster, one is about slower. Okay, so you can put all the things in reverse. Okay, and phase, we have to talk about in phase and out of phase. In phase means the peak value goes arrive at the same time. The peak value arrive at the same time. It is in phase. Okay, and out of phase, the peak does not goes at the same time. Okay. So so you may challenge A. Are there any words saying talk about we have a two different frequency? No, all the phases talk about is in the same frequency. Okay, same frequency. And we have a special term for out of phase. A special case is anti-phase, which means the two this diagram, the lower diagram. Okay, the two phases goes in different directions, which is exactly 180 degrees difference. Okay, so at this point, the two waves, if they have a same amplitude, they will cancel each other. This is we call out of phase, anti-phase, which is a special case in out of phase. Okay, anti-phase. So you have to memorize all the terms if they are ready to ask you. Okay. So if we have a sine curve in phase, the amplitude will just double or add up. Okay. If it is 180 out of phase, anti-phase, the two phase having the same amplitude will cancel out. But if we have different phases or in different out of phase, but they are not anti-phase, so you have a new phase having a new phase, which is a complex waveform. Okay, so you know that waves can be added up or cancel out each other. I have to add this slide in is because I want to tell you that all our waves can be reduced into a sum of sine wave. Okay, all the phase can be reduced to a sum of sine wave. So you see that at the left side we got a we call it a square wave. Okay, we call it square wave. So actually you can see that it is a multiplication. It is an addition of different sine wave, pure sine wave. Okay. So if you have a complex waveform, you can do a Fourier transform and convert it to the frequency domain. So you can separate all the frequency out. But I'm not going to go talk to Tip about that. You'll learn it in your university. Okay. Let me grab the water first. Let me have a very quick break. So we'll go to the electric components, capacitor and inductor. Finally. So why I have to talk about the AC current for such a long time is because actually AC is same as the frequency we use when we are talking on the radio. Last time Last time we have just talked about we have our audio and we need a carrier wave to transmit our signal, right? So the carrier wave is just a very high frequency wavelength, okay? So when we trace all the peaks of the carrier wave or the added in resulted wave, okay, the resulted wave, our voice at the carrier wave become a new wave, right? We have just talked about the new wave. For this resulting wave, when we trace all the peaks together, we can recover our voice. This is how the radio works, and in Chinese we call it 点播. Okay, it's actually tracing all the peaks. Okay, so you know that your signal looks like it's very ugly, your carrier or your resulting wave. So actually it is a sine wave. It's an alternating current. So you know that we got a very high similarity between our AC we use daily and the resulting wave for the radio to transmit. They're actually the same thing. So that's why we have to talk about, it is a must for me to talk about AC. We can't skip it. Otherwise you miss this kind of phasor, you miss out the RMS, average value, peak value, and the frequency stuffs. Okay, they will be asked in your exam. So if you feel that this part is very hard, so you know that it's actually for your reference. We don't need it in the exam. But this diagram, you will have to memorize it. It will be asked in your exam. Okay, the RMS, how to calculate the RMS? RMS is 1 over root 2, peak multiplied by 1 over root 2, average value, peak multiplied by 2 over pi, and peak is 0 to the peak. Peak to peak is highest minus lowest. Okay. That's why I have to give you a single graph for you. This is all the conclusion you need. Okay. Oh, I'm actually thinking if I have missed any slides in this last lesson. I guess I have some parts I haven't go through yet, right? Let me just go through it in a very quick time.
Those at the end you missed.
Yeah, I guess I have like 20 slides haven't talked about in the last lesson. Let me just copy it. Oh, that's why I found a bit weird. Let me do the slides now. Let me just go through it here now. I guess I haven't. Wait. Oh, how come? Hey. We'll do some math first. Okay, we'll do some math first. Okay. Let me go through it in less than 5 minutes. Okay. Actually, they didn't ask you in the exam, but you, when I take my exam, I see these kind of words in my exam, but actually they don't You will know that the answer is not one of these. Apparently, Kirchhoff's, I always don't know how to pronounce this one. Kirchhoff's law, should be Kirchhoff's law. Okay, Kirchhoff's current law. They tells you about if you have a parallel circuit like this, all the currents in every branch, when you add them up, you are equals to the input of it, original input of it. Okay. And for Kirchhoff's voltage law, you know that in a looped, which is in a series circuit, a loop, the voltage must be the voltage of every component, the potential difference in every component will be the same as the voltage of the source. Okay. That's why I have to talk about it is because if you don't know these two laws, it will be very hard to explain why we have to deal with this first. Okay. So for your calculation, we got a diagram like this, right? Let me just put it. Let me just do some math stuffs. Just a minute. Hey, help me. Yes. So you know the answer, but I have to still talk about it. Otherwise, it is part of your exams questions you will meet. Hey, how come? Just a minute. I haven't do anything yet. Just let me open it my iPad. I need a drawboard. Can I? No, I can't. How come? Hey, never mind. I just don't have to use it. I don't know why I can't show it. Never mind. Let me just explain it on the whiteboard. Okay. If we have a circuit like this, so we have to calculate. You have to calculate R2 and R3 first. Okay. R2 and R3 is a parallel circuit. So you know that for a parallel circuit, only the I will varies. Okay, only the I will varies. Kirchhoff's law tells you that the voltage of a loop is equals to the source, right? So that's why the voltage will drops across R1, and this is the R2 and R3. At this black point, the voltage is the same, and R2 and R3 will have the same voltage across them. Okay, this is from KVL, and let's go a bit deeper. Okay, so if we have to find the current of the whole circuit, how can we do it? We do it R2 and R3. So what is the resulting current, resulting voltage of R2 and R3? What is the resulting resistance of R2 and R3? So it will be 1 over 2000 plus 1 over 1 over 20,000 plus 1 over 80,000, right? Let me see if I can really. Okay, I can't. Never mind. Let me try it once again. If I can't try it once again, I will just use my whiteboard. Great. Let me just do it. So you have this in your notes, in your PowerPoint, right? So I'll use it. Great. So actually we now have a current like this. We have a great. Can all of you see this? Great, you can see this, right? Okay, so actually works. So I will use my iPad next time. So you have a circuit like this, right? You have a circuit like this. So you have to first analyze this part. You have to do with this part first. So you know that the current, the voltage across these 2 points, the voltage across these 2 points are the same, okay, by Chekhov's law. So we have to calculate this resistance first in parallel. So what is the resulting resistance? It is R equals to what? 1 over 2,000, 20,000 plus 1 over 80,000. Okay. So what is the value? It will be. Can anyone help me to calculate this, or otherwise I have to take my Excel out? Never mind. I will just take my Excel out. Excel is a good tool. Plus 1. So the value will be 5,000 and okay. So this part we can change the circuit into this way. You now have a battery here. This is once again 5,000 ohm, right? And you can change the circuit into this one, which is 5714 ohm. Okay, easy, huh? So for this two 5,000 and 5714 ohm, these two resistance is connected in series. Yes. So how to calculate resistance in series? So you just adding them up, right? So you know that the battery here, and you know that the resistance will become 10714 ohm. Okay. And what is the voltage of it? Voltage is 250 volts, right? So what is the I? I equals to what now? So by Ohm's law, we know that Ohm's law is V equals to I out, right? What is V now? V is 250 volts. I will just give the unit. I times 10714 ohm. So you know that I equals to 0.0238. Because I calculated yesterday, so I still remember this. It should be around 23 yes, 23 milliamp. So this is how you calculate this kind of circuit. So this kind of circuit is already the most difficult part in your resistance calculation. So if you know how to convert this circuit into this one by one, then you score at least 2 to 3 points. Okay. Why I say 2 to 3 points is because they may not asking you current directly. Okay. Sometimes may trick you, like this one. What is the voltage across resistor R1? So how can I calculate it? So you have to make use of current voltage law, Kirchhoff's voltage law, right? Okay. So let's go on. I will just leave R2 and R3 for your exercise. I'm not going to go through it. Okay. Okay. So we have a circuit diagram like this. What is the voltage across these 2 points? I have to calculate what is the voltage across these 2 points. So you know that what is I? I is 0.0238, right? So actually we can convert the circuit like this. Okay. So you know, once again, V equals to I out. You know that for Kirchhoff's current law, you know that the total current of 250 is the current on these 2 points plus these 2 points, right? It is because here is because V1, here is because V2. Okay. So how to calculate it is, once again, we make use of what V equals to I out once again. So for this resistor R1, V is unknown, right? I is equals to 0.0233A, and current is, and resistance is 5,000. So you just multiply these two values together, and you know why. You know how. It should be 1, 2, 3. 16.7. No. I'm not sure. Let me just grab my calculator out. Equals to 0.0233 times 5,000 equals to 116.666 B. This is how you calculate it. Okay. Okay. So let's just go back to our slides. So I have give you the answer of resistance 2, 3 in the speaker notes, okay? Okay, in the speaker notes, okay? So if you are not sure how to calculate the resistance of 2 and 3, just let me know in the WhatsApp group. Okay, I will do it manually. Okay, magnetism I've just talked about. So like poles repel and like poles attract. So a magnet will always point to the north pole at one point and south pole at another point. Always. It's because as the basic explanation is, do you know electron is like this, right? A moving charge. So they have an electric field. The moving charge is actually an electric field. So for electric field, moving electric field will generate a magnetic field. The magnetic field must have both ends, positive end and north pole and south pole. So you can't find magnets with a single pole. So if you find it, let me know, and we can share the Nobel Prize. Okay. Yeah. One of the research is saying that, oh, are there any magnets that has just one pole? They are really doing research on this. So, but in our daily life, we will say that every magnet will have two poles. Magnetic field, if we have current like this, we have a flux line. Okay, just to let you know, any wires carrying current will have magnetic field circled around it, and for the current flow from positive to negative, we use right hand thumb rule to find out the magnetic field. Okay, the thumb means the current flow. So okay, so in the diagram, the current flow from positive to negative, which is flowing in this way. Okay, so you know that the magnetic field will grabs like this. Okay, grabs in this way. Yeah. This to find out the magnetic field of when current pass through the wire. Okay. Inducing EMF. When a wire pass through a B field, pass through a magnetic field, or we say B field, we can have induced current in it. Okay. I have to talk about the Faraday's law of induction. So not that important in your exam, but you know that when you move a magnet into a coil, the coil will try to generate a magnetic field against the movement of the magnet. Okay, this is the Faraday law of induction. Okay, so you have two results. The first result is you have induced current through the wire, and the second result is the induced current will generate opposing B field against the movement of magnet. So if the magnet is already in your coil, it will do the same thing. Prevent the coil from leaving the coil. Okay. Right hand rule, I have talked about it. How come I forgot the power? Power, easy. Just current times voltage. It's a measure of how much energy is used in a circuit. Okay. So especially like if current flow through a resistance, some of the power may be consumed as heat. Okay. They find it as a rate of the work being performed. So you know that power is just voltage times current. So you just multiply these two values together. So it is the motor having a 48 volt, W-A-T-T, volt power, watt power, watt, okay, watt. Power equals to voltage times current, okay. But sometimes they may ask you the power efficiency. So that's you have to saying that, oh, what is the input of our current and voltage, and they may give you the output. Like oh, my motor is having a 30 watts. Okay, it's having an output of 30 watts, but your input is 48 watts. What is the efficiency of it? So you have to do some multiplication. 30 over 48 times 1000, times 100 to get the power. Questions like this, okay? And I may give you the question bank next lesson, because I'm going to travel tomorrow. So I may not have enough time to prepare the question bank. But the slides of next lesson is done. I finished the slide for next lesson. So don't worry. I have enough notes to talk about. So example, like if we have a 40 ohm resistance, how much power will be dissipated in a 400 ohm resistance if a potential applied is 200 volts. So how to calculate it? As we just talked about, P equals to what? P equals to IE, right? IV. We don't have the current here, so we have to use Ohm's law to find out the current first. Right? So we have some magic numbers. No. 400 ohm and 22 what? Let me wrap my 200 volts, right? 200 volts. 200 volts. So first we have to use V equals to IR, and actually this is a circuit like this. Okay. They ask you how much the energy is. What is the energy dissipated? Okay. What is the energy released as heat? How to calculate it? So you have to use P equals to IV, and you know that this important number I is missing. Okay, I is missing. How to find I? Once again, our old friend Ohm's law, V equals to IR. V is 200. Actually 200. 200 equals to I times 4000. So what is I? I should be 0.5, right? Let me use my... Yes, 0.05 ampere, okay? So P equals to IV. Now you know P have equals to 0.05 times 200 equals to 10 watts. This is how you calculate. Okay? So we can check our answers. Am I correct? I believe I'm correct. Yes, 10 watts. Okay? So you know how to calculate. Yeah. Okay. So we have finished all the stuffs about power and electromagnetic force, how to induce currents, that kind of stuff, and why the current by Faraday's law, the reason why we have an induced current to oppose the change of magnetic field. Okay, so we'll have to go through the capacitance in the later lesson. So let's take a 5 minutes break first. Okay, so we'll go through the capacitor. Capacitance is the measure, the unit of capacitor, okay? The measurement of capacitor. So we got Leyden jar here. So Leyden jar is, do you know what is Leyden jar? I guess some of you should see it in your high school physics, okay? No, you can see it, okay? So actually, Leyden jar is, or if we connect it in this way, we call it a Leyden battery. So Leyden jar is actually a very old style capacitor. Okay, so capacitor, we got charge on one side. So you see that in a Leyden jar, it is separated in a flow glass. Okay, separated flow glass. So the inner side with a metal coating cannot be connected with the metal coating on the outer side. So when we give electricity in it, the charge will, it depends which charge you give them. The charge will stay on one side, so you have different charges on different sides. So if we connected this inner coating with the outer coating, the energy will be released. The charge will move. Okay, so this is how Leyden jar works, which is the very fundamental capacitor, very old capacitor. So if you know, so in other words, if you know how to make a Leyden jar, so you can store some electricity in emergency. A plastic cup with two metal foils inside and outside, so you can store energy with a plastic bottle. Okay. So, but sometimes Leyden jar, if you do the secondary school physics, you see that sometimes it may connect it to a Van der Waals generator, electrostatic generator. So I'm not going to go through this. Just continue on our capacitor. Capacitor, so I've just mentioned, we've got two metal plates here and insulated. So if we don't have any other materials inside, we call it air dielectric. We use air to separate the two metals pieces. Okay, so by changing the metals in between, you will have a stronger permittivity, so that we can store more energy. Permittivity is not asked in your exam, but I have to go through it because there are some concepts you have to know. Okay. Charges. Okay. So application: coupling, transferring, bypassing AC current. Yes. And blocking DC current and blocking DC voltage. So we use it as filter. We call this kind of capacitor filter capacitors. I'll explain why it can block DC.
You skip a page. You need to go back a page. Explain what is a capacitor first. No,
let me go through bit by bit. Capacitance, Leyden jar, this one, capacitor, air dielectrics.
Okay.
Yeah. So air dielectrics, what I mean is, if we don't put any stuffs here, we just use air, and we call air dielectric. But if we put other solutions in it, the permittivity will change, so that it can store more charges on both metal plates. Okay. So this is how a daily capacitor is used. So I will explain it in later slide when we talk about different types of capacitors. Storing energy. So I have to go to the next slide first. Why we can store energy? So capacitor actually looks like a water tank. We fill electricity in it. Okay. So when we use it, we just open the tap and the energy will be released. So this is how a capacitor works. So in a DC current, we don't have any alternating, right? So we just put energy in. We can't take energy out. So that's why we can say that blocking the DC voltage. It blocks. You see that if we connect a battery in it, inside it is insulated, right? There are no electricity can connect, no conducting pieces between these metal plates, so it will not conduct electricity. The current will blocks. Okay. And apart from the DC current, we will talk about the low frequency electricity. Okay, so I'll just talk about the tuning circuit. So it can help to tune your radio by choosing the correct frequency. We will talk about it when we talk about LC circuit. We are not going to talk about it now. Yeah. So it have to it will be can be used when we cooperate capacitor and inductor. Okay, capacitance notation C, unit farad. It helps to measure the ability to store electrical energy and electrostatic field. Just think it as a water tank. Capacitor is just a water tank. Okay, it helps store the charges in it. Okay. Helps store the charges. Okay. And okay, these two slides, I must tell you that you don't have to memorize it. And even in PK short notes, they are not going to tell you this. But you guys are more advanced students, so I can provide you more knowledge in it. So permittivity, it's okay. So in this diagram, you can see that here is what we call not vacuum, but free space, okay, or air dielectric, okay. So you can see the charges is on these two sides. So this is the weakest capacitor we can have. So if you have different materials here, these materials will also polarize, but not conducting the electricity, so that it can help store up more charges by just changing this layer, dielectric layer. Okay. And the permittivity is the measure of polarizability of a dielectric. So higher permittivity, more charges can be stored. Lower permittivity, less charge can be stored. Then the notation is epsilon. So the permittivity of free space is denoted as epsilon, not epsilon naught or epsilon 0. So epsilon 0 is one of the constants you can choose in your calculator. Yeah. Or in Chinese we call it 真空電容率, free space permittivity. 自由空間 okay, I should put it this way. Free space permittivity, 自由空間電容率. Okay, so even in free space, we can store some charges in it. Okay, but if we try to change these materials, charges, we can store even more charges. Okay, so there are some different variables in the capacitors. How can we alter capacitor? First, so you can see that C is epsilon naught A over D. Okay, so if we have a lower the spaces between the metal pieces is shorter, so you know that charges attract each other, right? The attraction force will become stronger and stronger, so that the capacitor will increase, the capacitance increase, okay? Because the attraction force is stronger. So if you put them apart, the attraction force is weaker. It's because capacitors, you know the charges, right? Different charges will attract each other, okay? But if you have a larger spaces in between, the attraction force will decrease. So that's if we have a less space, the attraction force will increase. And if we have a larger place, we also have a larger surface area, we will also have, it can take up more charge. So that's the capacitance also increase. Okay. The first part is changing the dielectric layer with a higher permittivity one. Okay. So you can see that. But actually, if you can't memorize the permittivity, just memorize a capacitor can be altered. Value of capacitance can be altered by the size of metal plates and the space between it. Okay. So in nowadays, the capacitance actually they rotate, they turn the metal piece into a very small coil in a spiral shape and put it in the capacitor. That's why all of them looks like a metal can, a small metal can, right? It's metal cylinder. It's because actually it is paper sheets rotating in this way inside your capacitor. It really looks like it if you open it up. Okay. And by doing so, you can have a very, very large surface area, but with a very small volume. It can help you save up some space. Okay. By changing the A, you okay, in original it is very big, right? A very big piece of sheet, right? A very large paper sheet. So if you rotate it, the cross-section area becomes smaller. So it can store in a smaller place. But the surface area remains unchanged. Easy to understand, huh? Okay, let's continue. Okay, so as I just talked about, the DC currents will be blocked. Okay, once again, this is for your reference only. You don't have to memorize it in your exam. It is for your concept. Okay, for your concept. We have a capacitor here, and this is apparently this is a DC because we connect the circuits into a battery, so it is a DC. When we close the switch, you see that the electricity at the E, which is the voltage, will grow up in the curve like this, in a log scale, okay? And the currents, you can see that at first it grows up very quick, and when the capacitor becomes saturated, the currents will go slower and slower. Because you don't have a very high potential difference to keep on giving the current to the capacitor. Okay, it's called saturated. Okay, so if we discharge the we opens this charge and close the charge, so that the capacitor will discharge. At first, the current, the voltage will at a certain point and will drops in a log scale. Okay, and you see that the current flow is actually a bit slower. The voltage leads the current, and this is a very important characteristics in capacitor. You have to know that the current move faster than the voltage move faster than the current by 90 degree. Okay, voltage leads current by 90 degree. Okay. Correct me if I'm wrong, huh? Okay. Yeah. If you know I'm wrong, just let me know. Okay. So we have some more calculations. Capacitor. Capacitor is different from resistor. Resistor, in series, it is adding them up, right? Parallel. Resistor is one reciprocal of it, sum of reciprocal, right? But in capacitor, you think it is a water tank. So if I connect the capacitor in this way, that means you can think I have 3 water tanks to collect the water at the same time. I can parallel the water tank, right? So that I can choose each tank to store the water. But in this way, if I just told you, when one capacitor is filled, it is already an open circuit. So the capacitance in it actually drops. So capacitor in serial, it looks like the calculation of resistance in parallel. But in parallel, it is just in the reverse way of resistance. Okay, they are flipped. Very important. If you do your calculation, don't make it wrong. It's different. Okay. And okay, so I will move on to the calculation now. Let me see if I have a good space. Oh no, I have to reconnect it once again. Oh yeah, good. My screen come back. Okay. And example, if we have this diagram, the capacitors connected in parallel, you have a much larger capacitance in resulting capacitance. Okay, but in this one, you see that it is 1 over. How to calculate this one? Let me draw my diagram first. What is the value? Hey. 0.01 mu f, and this is 0.02 mu f, and this is 0.05 mu F. Okay, I have finished drawing my circuit. Okay, we have a circuit like this, right? So actually, you know how to calculate it. The C will becomes 1 over 0.01 mu F plus 1 over 0.02 mu F plus 1 over 0.05 mu F. Okay. And remember that mu is 10 to the power negative 6, so you have to make a change. So when you put it in your calculator, you will know that, hey, okay, so this is the resulting capacitance. So I'm not going to show how to do the fractions. I'll just give you the answer directly, because doing the fraction is a torture. This is 0.059 mu F. Okay. So sometimes you may argue, hey, I'm by connecting in this way, the capacitance is decreased, but the use of capacitor is just storing the energy. How come I want a circuit having a less energy stored, right? It is not. I can just choose a single smaller capacitor directly, but I have to connect it in parallel, in series, right? Do you understand what the question is? Yeah. Okay. It's because if you connect the capacitor in this way, they can withstand a higher voltage. Okay. That's why sometimes you may sacrifice the capacitance, but the overall circuit can withstand a higher voltage. Oh, yeah, I'm really wrong. Luckily, I have this slide with me. Yeah, voltage lags current by 90 degrees. Remember this. I'm wrong at my first two slides. Voltage lags current by 90 degrees. What is, it means that current goes first and voltage follows. Okay, so they actually got the phrase here, CVO, right? CV lags I, okay? CV lags I. And L actually is the, L represents inductor. So it is VIL. So which means current lags voltage by 90 degrees. Okay, so voltage lags current by 90 degrees. In other words, we can say that current leads voltage by 30 degrees. Okay, if they don't give you the word lags, and they give you leads, you can still distinguish which one go first and which one goes back. Okay. Ohm's law for reactance. So all the electronic components, they got reactance with it. I'm not going to do the complex math, but you can know that impedance is the result, after a very complicated calculation, result of resistance and reactance. So reactance is part of somehow part of the resistance because of the phase difference. Okay. Yeah, it is the resistance because of the phase difference. So we usually denote it as X. Okay. So for capacitor, they got a capacitive reactance, which is we call XC, and XC is equals to 1 over 2 pi FC, which is directly with an inverse of capacitance and frequency. Okay, so you know that XC is directly proportional to 1 over F, which means when frequency is very low, reactance will become very large. Okay, let me grab this board with me. Ah, very good. That's why I have to bring my iPad so I can draw any stuff that I want. E pi 2 pi fc, right? So when xc goes up, 1 over f also goes up, which means f goes which direction? Yes, f goes down. That's why we call when we have a very low frequency, the reactance is very large. But in other words, if you have a very high frequency, the reactance is very small. Okay, which we have a formula to denote it. Okay, and capacitance. Oh, you know the C. Okay, you must have to memorize this question. They must ask you this one. But in which form, I'm not sure. In either just calculating the capacitor or ask you the LC resonance circuit, I'm not sure. Because they may make up all the mix all the stuff and ask you in just one simple question. Example, okay. So voltage. If you have a voltage across a capacitor of 200 mF at 7.5 MHz, if current is 50 mega amp, what is the voltage of it? Okay, so for this question, it's just like this. We got just a minute, let me grab my excuse me. 200 pf. Okay, let me grab my this one. They want to ask you what is the voltage. Okay, right. So how to calculate it? Simple. So you have to use two calculations. One is, you know that xc equals to 1 over 2 pi fc, right? One is v equals to I r or ix. Okay, so you have to use two equations at the same time. Okay, so we deal with the xc first. Xc equals to 2 pi, f is 7.15 times 10 to the power 6, and c is 200 times 10 to the power negative 12. So in capacitance, you always meet units like micro, nano, and pico. So you have to memorize the SI units, because they may not give you this kind of notations so that you can easy to calculate, but they will just directly give you PF. Okay. So what is the XC? I don't want to calculate it. Can somebody help me to calculate it? Never mind, I can calculate it on my own. Okay, so with some calculations, you know that the capacitive reactance is 111.14. Okay, so by again V equals to I out, right? You know that the current is 50 milliamp. 50 times 10 to the power negative 3, right? And times 111.1448. What is the value? So you can continue to calculate. 50 times 10 to the power negative 3 times our, which is 5.56 V. Okay. Let's check the answer. Am I correct? Really, I didn't prepare for the calculation. I just, yes, 5.6 V. They got round up errors, so that's why there has a little difference between my answer and the correct answer. Yeah. So you know how to calculate this one, capacitor. So that's why we always say that they can ask you a lot of questions about Ohm's law, but they can apply Ohm's law in different methods, like capacitor, like LC circuit, or like inductors. But actually, if you know all the formulas, you can boil down to V equals to I out. All the things is V equals to I out. Okay. We got different types of capacitors. The most common one is the mid-cut capacitor. Paper capacitor is also can be seen. Actually, if you go to open up a PCB, a circuit board, you will see that electrolytic capacitor is the most common one, and it is the type we just. Why it is in a circle cylindrical shape is because it rolls up the metal sheets in it. Yeah. And the most important thing, the most important characteristics of this capacitor is you cannot flip the charge. Okay, they mark a negative cathode on it. If you accidentally flip the connection, it will blow up. Yeah, they got YouTube videos. Try to do it on purpose, blow up the capacitor on purpose. Yeah, and all the electrolytes will just fly away. And variable capacitor, you will see that in your auto tuning units in later time when we talk about measurement. They got different metal sheets in it, and so you rotate. When you rotate the knob, the metal sheets will cross over each other, and this can change the capacitor. Yeah, which helps to tune our equipment. And they got different symbols. Polarized capacitor, they got a plus here. Non-polarized, they cause just two thick line. Okay, for variable capacitor, you will see an arrow or have a stroke over it. Okay, yeah. So if you see the polar capacitor in your circuit diagram, you know that you cannot invert the capacitor in any means. Okay. Reading the capacitor, when PK told me, just for your reference, we are not sure if they ask you or not, but we'll just teach you first. Okay. Capacitor. You may see that sometimes they print 104 in your on your capacitors. Let's see if I can bring my sets of equipments to you next lesson. Because I have already bought some capacitors from Taobao. I can show you the real piece. Yeah. Last time, yesterday I've just showed the secondary school students, but I forgot to bring with me today. Okay, 104, the first two digits means just the first two digits, okay? Same as resistance. The last digits is a multiplier, 10 to the power number. 1004 means 10 times 10 to the power 4, okay? If it is 314, then it is 31 times 10 to the power 4, okay? As simple as that. But if for a larger capacitor, electrolytic like this one, they will directly print the capacitance on it because they have more space on it. This is for limited space. Printing 3 letters to represent all the stuffs. It's okay. So if sometimes they may have a very weird naming, like 4N1 and P45. So P45, you know that it is P at the first, it is 0 point decimal. P means pico, N means nano. So 4N1 means 4.1 nano F. Yeah. Let's see if I can finish my inductance slides today. Let me have a quick check. Yes, but I'm not sure if I can do the LC circuit. But never mind, we will have the exam on 11th November, right? So I have some more time to talk about it. We have some more spare time. Inductance. So once again, right hand thumb rule, but moving current in over a wire will have induced magnetic field. So we make use of this induced magnetic field to do our inductance, like our how should I address it? Transformer, right? Transformer is just two coils matching each other. So it is using the Faraday's rule, induced magnetic field, and one coil accepts the magnetic field and generates the current. Inductor, a simple inductor, this is one or more turns of wire. So by having more turns of coil, it can amplify the inductance. Okay, that's why usually it is in a solenoid. Yes, and it can also help to transfer an energy or do the copulation. And there is really one interesting usage in industry is when you have when you want to transfer energy to another pieces and you don't want they are directly connected, you use a one-to-one transformer to transfer the energy to another piece, so that when the circuit is shorted, they don't affect the rest of the part. Yeah, this is a very special point of inductor. And inductance, magnetic flux. I've just drawn to you, right? This kind of stuff. Okay, and so you know that a coil, its nature is just a long wire, right? A long wire. So that's why when you close the circuit, they have induced magnetic field. It doesn't matter if it is just a single wire or if it is a coil. They work in the same way. Also have induced magnetic field. Okay. And example and symbols are all the inductors look like this. At least they have a metal coil on it. We have different variations: air coil, variable, and or magnetic iron core. So that's you know that all variables have a stroke on it, and for iron coil, they have two straight lines near it. Sometimes we have to add an iron core because we want to increase its inductance. Okay. Just a minute. The reason why I have to show you this formula is because I want to show some variables in the solenoid in the inductance. Okay, the inductance can be altered by some parts. The permittivity, okay? So I'm not going to go through the permittivity, but you can think it is, if we insert the iron coil, we can increase the permittivity so that it can help to transfer more energy. Yeah. Cross-sectional area. If we have a larger coil, we can have more inductance. And you have number of turns, so that actually you can think it is a long piece of wire and we compress it into a solenoid so that we have more wires. More turns mean that a longer wire is used, and that's why you can have a higher inductance. Okay. And the cross-sectional area, if we have bigger coils, they can accept more energy. Okay. Think in this way. But actually, I don't think they will ask you in exam. Once again, but if you have two coils in hand, you can note which one is strong, is having a higher inductance immediately. And transformer is an example of inductor. Do you know what is transformer is? Transformer. 邊人咁講? How come no one is laughing at this joke? Transformer, so that it can help to this is actually a microwave. I copied it from YouTube, and it is we call a step up transformer. So that our electricity is using 220 volts, but microwave will need higher voltage, like thousands of voltage. So we need to have a step up transformer to increase the voltage. And actually, the voltage, how to increase the voltage is using coils, using inductance. Self-inductance. Self-inductance means eddy current in it. The coil in it, you can think that when we amplify the magnetic field by changing the straight line into a solenoid, the wire in it still have induced B field. So these two B field will affect each other. Okay, so it is called the self-inductance. Okay, and for mutual inductance is more widely used. We have a power supply here, and we can think in this way. It is it is coil, and this can they have an alternating B field, right? The magnetic field flux will cut through the second coil, so it can transmit the energy to the second coil. Okay, second coil will receive the energy and drive this circuit. This is called mutual inductance. So mutual inductance will cause two parts: a coil connected to a power supply, and this coil will transfer the energy to the second part, and the energy will be delivered to the circuit board. And for this diagram, we call it is gapped or insulated transformer, so that these two parts can be isolated and you don't have to worry about the electric shock. Yeah. Okay. Applications. Tuning circuits, it's okay, and when we have to apply it with capacitor, sensors, storing energy. Yes, but I'm not sure how to store energy. I see there are some circuits using inductors to store energy, but it is not that common. Capacitor is more common, but still you can store energy with it. Motors, AC motors, transformer, filters. I have to explain why filters can be used. Okay, the rest I'm not going to explain it. Okay, so analogy. Actually, the inductor is just a rotor. Okay, when the current passes through it, the rotor will move. Okay, but think in this way: if I have a very high frequency AC, the water flow will keep on switching its polarity, right? So the rotor will, which direction should it flow, right? So it will have a very high reactance, a very high resistivity. The correct term is reactance, but I would use the word resistivity to resistance to let you easier to understand. Okay, so that's why when the voltage is a very high voltage AC, the inductor will have a very high resistance to prevent the current change. Okay, just think it's a rotor and it can help to deliver the energy. Inductors, it is notation is L and the unit is Henry. Okay, H, Henry, H. So that's why why they teach you CIVIL, C-I-V-I-L. It's because L is represent inductance. Okay. Once again, CIVIL, VIL, right? So the voltage leads current this time. And for capacitor, it is current leads voltage. Okay. So this is a very brief introduction for you, saying that when the circuit is closed and when energy is delivered, how will the current change at any instantaneous point. But don't worry, you don't have to learn it in exam. It is just for your reference. Okay. Okay. So every conductor has a resistance, right? Same as resistance, the inductor is just a very long metal piece. So that the inductor, we can just think in this way. Inductors connect to each other, so the inductance will increase, just like resistance. And when it's parallel, it will separate down. The inductance will split up. Okay, will split. Actually, if you memorize this one, the coil followed by coil, so have 3 connected coil to receive the energy at the same time, it will be easier for you to understand why it is L equals to L1 plus L2 plus L3. And capacitor, think in the parallel way. 3 different ports to store the energy. Yeah. Remember this one. You will need it in your calculation. Actually, it is same as the calculation as resistance, so I'm not going to do the calculation once again. Okay? You can just add them up. Voltage leads current by 90 degrees for inductor, VIL. Don't ask me why. It is about the phase change, and you really need more complex math to understand it. It is about how you need to learn about the complex maths. Really, the complex, the imaginary number to explain this one. Inductive reactance, it is very easy to understand. It is 2 pi FL. 2 pi FL. Okay, and so you see that XL, inductive reactance, this time is directly proportionate with F. So that's when F frequency is very large, the XL will be very large. Okay, so it likes DC more. Okay, the inductive reactance goes down when the frequency is very low. Okay, very low. Okay. So thinking this way, if it is DC, it just acts like a piece of conductor, right? Just a solenoid, copper wire in solenoid form, in DC. Okay. Can I just leave it for example? Okay. When we have a current go through a 0.H inductor at 130 Hz, what is the current? Okay, once again, I can give you some hints. If you know how to do the capacitor, using the XL equals to 2 pi FH and Ohm's law V equals to IR, you can know the answer. And the answer is actually here. 69.6 milliamp. Okay, it's okay. You can get the answer and calculate it at your home. Okay. This is actually. Okay. So you can do the answer. Then double check at home. You know how to do the math, and I will just leave it there. We have how many times left? Great! We can finish the slide today. Great. Impedance. So we have to talk about the resonance circuit. Resonance circuit in Chinese is called 調諧電路. Okay, 調諧電路. So impedance is a complex combination of resistance and reactance. So actually, this is the nature of AC. That's why they have a 90-degree phase change. So you don't add them up directly, but you do it in complex math. And why J is used is because in electronics, they use J to represent the imaginary number. Just because of this, if you do the math, you can just treat it as I. Okay, if you know how to do the complex numbers. Okay, so thinking this way, impedance is just root of R squared plus X squared. Do you have to memorize it? I don't think so. Just for your reference. And you may argue why XL minus XC. Actually, they have explanation, but you need integration for explanation. So I'm not going to explain it. But you see, huh? I have included lots of URL in my speaker notes. So you can click on it if you're really interested in knowing why the math is doing this way. Okay. But it is not important to your exam, just for your interest. Okay, at resonance circuit, we say that XL equals to XC when we connect this component together. So, do you need me to? Let me just calculate it once. So you don't have to memorize f, the value of f. You can just deduce it directly, real time. Actually, I didn't remember the formula. I just calculated it there. Okay. If I really have to deal with the resonance circuit. Okay. So at the resonance point, XL equals to XC, right? What is XL? XL is 2 pi FL, right? Or we say omega L. It's just the same, angular frequency, but I'm not going to talk too deep on it. XC is what? What is XC? 1 over 2 pi FC, right? So what is the frequency point? You can just multiply on both sides. 2 pi f square LC equals to 1, right? So 2 pi f equals to 1 over square root LC. F equals to 1 over 2 pi root LC. As simple as that. So you can deduce it when you have the exam. You don't have to memorize it. Just remember that the most important part is this one. XL equals to XC. Okay? This is how you deduce it. Easy, huh? Easy, huh? Okay. So we'll make use of the property of resonance frequency. Okay. But if you don't remember, if you can't do the math, you think the XL equal to XC, the deduction is very hard, you can just remember the second formula. But I would prefer it this way, because I think memorizing less equations is more helpful to me. Yeah. And LC in serial, okay? So when in serial, the impedance will become at the resonance point, the correct frequency, the impedance will go to the lowest, okay, the lowest. So if you think in this way, if it is the lowest, it will go to the ground actually. Never mind, I will just explain it later time. Okay, LC circuit, impedance at frequency point, impedance lowest, okay, but in LC parallel, the impedance will be highest, okay. Just some you have just memorize as hard fact. Okay. But actually, you will make use of this these properties in your exam. Okay. So it really depends on how you do the math. Okay. Like I really don't know how to explain this one. Let me. Okay. So sometimes if you have a LC in parallel, they use this one as a tuning circuit, the resonance circuits. Okay. So why we have a very high impedance is because we want to prevent the current flowing through this part. If this part have a very high impedance, the currents will flow to other parts if it is connected to in parallel, right? Just a minute. I think I see that there are some 迷茫 in your mind. Okay, think it this way. If we have a circuit like this, like this is 5 mega ohm, and it is 5 ohm. Which one will be larger, I1 or I2? Let me put it this way. I shouldn't use 5 mega ohm. I should use, let me put it this way, 100 ohm. Okay, this is 5 ohm. Which one will be larger, I1 or I2? It must be I1. Okay. You can put in some maths and try to do a calculation. Like I would say this one is 5 volts. Okay. So once again, Ohm's law. Ohm's law what did Ohm's law tell you? V equals to IR, right? I don't know what is the current flow through it, but let me make up a number. This is I. Okay. And I know that I equals to I1 plus I2. Why I equals to I1 plus I2? This is what KCL tells you at the very beginning of our lesson. KCL, okay? V equals to IR. And I know that it is equivalent to this circuit. 睇住時間，我講埋呢 part 我就 stop 啦今日。I will just end this lesson as soon as possible because I see time is running out. Okay, I here. Okay. What is the resistance of this one? The resistance R here is R equals to 1 over 100 plus 1 over 5, right? Okay, so what is the result? What is the 1 divided by 1? Just a minute, my Excel gone wrong. Okay. Okay, actually you can immediately know what is R. R must be in a range which is smaller than R's must be smaller than a number. Guess a number, give me a number. What R will be less than? You got two values here, right? 105, right? 105, 105. The resulting resistance must be less than which number? 100 or 5? You immediately know your resistance must be less than 5. Okay? Do I need to explain why? It must be less than 5. Think in this way. If you have a very big road, this is like 5 ohm, and a very narrow road, 100 ohm. Okay, so apparently you can have more cars to walk through. You got, even though you have a very narrow road. Okay, so you can actually, why the total resistance will be less than 5. Okay, 5 is already very large. You have a even have a extra road for them. That's why it must be less than 5. Less than 5. And the result is, okay, 4.76. So V equals to IR. 5 equals to I times R. What is I? Which is 1.05 ohm. Okay, so you now know that AI equals to 1.05 ohm. Okay, does it make sense? Okay, let's continue. So you know that I equals to this one. Okay, 唔係我咪調轉咗？唔係喎，冇調轉，冇調轉，冇調轉，冇調轉。V equals to 5, right? Yes, and then 唔係喎，你唔使計呢個 V equals to 5。I 係傻添，做咩唔提我嘅？I is actually so for I2, okay, this is I2. What is I? I is 5 over 100. What is 0.02? Is it 0.02? 0.05. Okay. And for V equals to I1R, 5 equals to I times 5. Okay. So I equals to 1/8. So you immediately know which one is larger. And the sum of it is just 0.105, which is I calculated earlier time. Okay. The voltage across these 2 points is correct, is constant. Okay. The voltage across these 2 points is the same. The voltage across the between the blue points and the green points are constant. Okay. This is how you calculate it. And because the resistance is very small, more current will flow through it. That's why when I talk about if you have these two resistance parallel together, you can immediately know which side have a larger current. Okay. So at the same time, if I have a just think it this way. If I have a impedance very large, okay, very large, and I connect it to a parallel circuit like this, very high impedance, less current will flow through it. Small currents will flow through to the remaining parts of your circuit. That's why it can be also choose as help to tune your frequency. Impedance high enough, more electricity more current flow through to the rest of your circuits. Yeah. And actually for LC in series is also the same. But why it's the same is because we try to lower the impedance of the whole circuit, so that you may parallel it with a very high ohm resistance, so that the currents will flow into your LC circuit. This is how you make use of the LC circuit in series, very low impedance, and LC parallel you have a very high impedance. Okay. We will leave this example to you and we will check the answers together next time. It is 12 megahertz and I will try to ask you how do you calculate it. Okay. So to sum up, what we have go through the 4.1, actually we have go through nearly most of the part 4 radio and electricity in our syllabus, and what's remaining is the semiconductors part. Okay, let me have a quick check. I really forgot what I have taught in lesson 6.